problem number 3, we have this vector field right here. And our surface is a part of the sphere, x squared plus y squared plus z squared is equal to 36, with these 3 boundary planes right here. And so let C be the boundary of our surface oriented in this direction, which I should point out this clockwise orientation is like the quote-unquote wrong way to do it. So I have to take that into account later on. So we are being requested to use Stoke's Theorem to find the integral over C of f dot dr. So what is Stoke's Theorem? What will Stoke's Theorem tell us here? It's equal to the double integral over S of the curl of f dot ds here. The flex of the curl of f over s. So the first thing we need to compute here, let's go ahead and compute the curl. So we're going to compute this instead. The curl of f, okay, I hat, j hat, k hat, partial derivatives with respect to x, y, and z, y, negative x, and 0. And what do we end up with here? Partial derivative with respect to y of 0, 0, minus partial derivative with respect to z of x, negative x is 0. Then we'd have the partial derivative with respect to, let's see here, partial derivative with respect to z of y is 0, minus the partial derivative with respect to x of 0, that's also 0. And then we finish this off with the partial derivative with respect to x of negative x is negative 1, minus the partial derivative with respect to y of y is 1. So minus 1 is minus 2 here. Okay, so now how do we parameterize this surface right here? So we're taking a look right there. Parametrizing part of a sphere, we can do that with r of phi comma theta is 6, because this is 6 squared there, so the radius is 6. 6 cosine theta sine phi, 6 sine theta times sine phi, and 6 cosine phi. Okay, there's our parametrization. Our normal vector here. So usually we do r phi cross r theta. I'm going to do it in the reverse order. We do r theta cross r phi. You end up with negative 36 sine phi times cosine theta sine phi, sine theta sine phi, and cosine phi. So why did I change the order here? Because now with this negative sign out in front, this the normal vector to our surface, we're orienting our surface so it's pointing inwards, in towards the origin instead of outwards like we usually do. And the reason for that is that we want it to be oriented inwards to match up with the clockwise oriented boundary instead of a counterclockwise oriented boundary. So that is how we're going to do it. There's different ways to account for this. You could just slap a negative sign on at the very beginning to orient your curve going counterclockwise. Many different ways to account for this. All of them are going to involve slapping a negative sign on at some step in the process. Okay, so here we have our normal vector. And what we would do is that we would take our parametrization, substitute into the integrand here, but this is a constant. So we're just going to do this dot product this. We're doing the curl of f dot product with r theta cross r phi here. So this dot product, this will be 0 plus 0. Minus 2 times minus 36 is 72 sine phi times cosine phi. Okay, so this is going to be what we are integrating. So we're going to be integrating 72 sine phi cosine phi d phi d theta. The last thing we have to take into account is going to be bounds here on phi and theta. So phi bounds are pretty easy. It's going to be everything from 0 to pi over 2, because we're going all the way down to the xy plane when z is equal to 0. So phi runs from 0 to pi over 2. But for theta, and this is the one part that could be just a little bit tricky here. So in the xy plane, we're going to start when x is equal to 0. Sorry, when y is equal to 0, that's the x-axis, and go until we hit the line y is equal to 4x. So right here, y is equal to 0, that of course will correspond to theta is 0. What angle is corresponding to y is equal to 4x? Y is equal to 4x, rearranging that would be y over x is equal to 4. And we should know that tangent of y over x, I'm getting this in the wrong order here. Tangent theta is equal to y over x, or theta is equal to the arctangent of y over x here. Okay, so what do we see here? Y over x is just equal to 4. And so our upper bound here is arctangent of 4. That's not something we're going to try to simplify at all. So what do we end up with here? When we integrate with respect to theta, we'll just get a factor of arctangent of 4. And when we integrate with respect to phi, the best way to do this is substitute in u is sine phi, du is cosine phi d phi. So an integral from 0 to 1 after we change the bounds of 72u du, and this will give us 36 arctangent of 4.